Right. Welcome back. First of all, fair warning, it's another one of those days where I'm going to have to take a 3-4 minute pause around 1 o'clock. So I'm sorry for that, but at least it'll only be a couple minutes. Second warning, we will definitely finish chapter 7 today, unless something crazy happens. Right. I'm just looking at my notes to make sure I don't have anything unexpected. Yeah, we should finish this section today, these two sections today, in fact, 7.6 and 7.7, which means that we can test in a week, except Thanksgiving is a week from now. Well, the Wednesday before Thanksgiving, but that's also a holiday for our calendars. It wasn't a few years ago, but it is now, so that's nice for the students. Which means I can't make the test next Wednesday and Thursday for very obvious reasons on Thursday, another as well, in my opinion, obvious reason on the Wednesday. So your test is Monday the 30th and Tuesday the 1st. Now, even if we don't finish chapter 7 today, if we finish it on Monday the 23rd, that would still give you a week between material and test time. It'll be pretty similar to the first two tests, somewhere in the ballpark of 20 questions, maybe a few less than that. There will be a review in the same kind of order as before. It'll be similar. You are allowed calculators. Because with this vector stuff, we're going to start having to round some things. When we were doing the law of sines and cosines, we had to round some things, and my math lab is going to need you to round some things. So you will definitely need a calculator for this test. So please, please, please make sure you have one available. If you're relying on the calculator on your computer, sometimes people struggle. You might be on a computer that has a lockdown browser. If you're like at a library or something like that, it only allows you to have one window open at a time. So if you're going to be in that situation, make sure you have a calculator physically and not the one on the computer. So just understand your circumstances. I'm not going to go and give you another attempt on a test because you didn't know your circumstances ahead of time. Okay, so let's get back where we left off. Last thing we did was example 4. Just really quickly readdressing what vectors are. They're arrows. These are things that have size and direction, not just a size, not just a direction. So the length of the arrow is important. It signifies how large that value is. And there's a lot of math that deals with vectors moving forward in calculus and differential equations, et cetera, et cetera. We have this symbol, the bold or the arrow means that something is a vector. The double lines around it means that that's going to be the magnitude. It's kind of like the absolute value, but we're talking about multiple dimensions and not just one, so it's Pythagorean theorem to get to it. We've talked about how we can take a vector and put it pretty much anywhere we want as long as we don't change its length or direction, and that we like to talk about vectors in standard position. So if they start at the origin, the A's and the B's in front of the I's and the J's tell you how far right and up to go or left and down or whatever. We talked about how it's pretty easy to multiply a vector by what we call a scalar, which is just a regular number. We said you can also multiply vectors by vectors, which there's two methods of that. One we'll get into, one we won't today. Adding and subtracting is pretty much as easy as your third grade math. We showed visually what it means to add vectors. I also showed you visually what it was to subtract them, but I erased it because it's less interesting. We talked about unit vectors being a length of 1 like the I's and J's, but they can be in any direction, and quite often we like to have unit vectors in the direction of what we're already pointing, because then we're thinking about relative to what that vector or us is doing, not just going right and up or left and up, just going, this much in this direction. So it's like having your own little ruler in the direction of the vector that you're going, instead of having the rulers only on the X and Y axis. There are a decent amount of formulas that you have to memorize from this section as well as the next, like how to get a unit vector. That's one of them. Writing things in standard form, you can argue that's one of them as well. Let me just bump this down. Way down. Okay. So the last thing we do is example 4. So we're up to this. If you're given magnitude of a vector, and the direction, the angle, theta, then standard form of the vector is, this is going to be your vector v will be equal to the magnitude times the cosine of the angle times the I vector plus the magnitude times the sine of the angle times the j vector. This is an extreme, oh, that someone knocked on my door instead of rung and it threw me off. It startled me. All right, where was I before I got startled? This is a really important formula because sometimes we're given the length of the vector and the direction that it faces, and you're more interested in breaking it down into components. Previously, we gave you the components, and those enable us to find the magnitude and the direction. Now we're going to be given the opposite set of things. We're going to be given the magnitude and direction so that we can label the vector in standard form. So if you wanted to break this down a little further, what this says is, your standard form was, ooh, that didn't work. V equals AI plus BJ. So what that says here is that the A, the x component, is the magnitude times the cosine of the angle, and B, the y component, is the magnitude times the sine of the angle. Think back to the unit circle idea. Think back to when we're talking about grabbing the coordinates on the unit circle to do a sine or cosine. We said sine goes like y, cosine goes like x. Well, here, your cosine is in the x component, and your sine is in the y component. The only thing that's different there is you've got these magnitudes, these lengths attached to them. So what's going on here? Why does this work? So we're given this distance right here, which is the magnitude. So this is our vector. If this is our starting point, this is the ending point, the terminal point of the vector. And then we can draw a little right triangle out of that where we call this A and this B. And then, of course, this would be the angle that the vector forms. Now, if this was in another quadrant, it would be a reference angle, but we can go between reference angle and angle quite easily. We've done it many times. All we're going to do is the absolute basic trig on this little triangle right here to prove that A and B are those. So the proof. Okay. Here's the triangle, here's your vector. Again, I put it in a quadrant 1 kind of order, but 2, 3, or 4, it would just be a reference angle instead, which wouldn't be a big change. Well, we know that the sine of theta is the opposite over the hypotenuse, which would be b over that magnitude. If you just multiply both sides by the magnitude, you'll get that the magnitude times the sine of the angle is equal to b, which is this right here. It says that the y component of a vector is the size of the vector times the sine of its angle. Similarly, if we do the cosine instead, cosine of theta, that would be adjacent over the hypotenuse, which is a over the magnitude. It's nothing new, just different letters. Guess what we're going to do? We're going to multiply both sides by the magnitude so that we get the magnitude, the length, times the cosine of the angle is equal to a, which is exactly what this says. The number one mistake people make here is they swap the sine and the cosine. They just think sines go before cosines. No, sines relate to y's, cosines relate to x's. This leads us into a very important concept of physics when we're talking about things involving angles. When you want to talk about dynamics and statics in an engineering concept, very, very, very important. When we want to talk about static forces, frictional forces, all of those, kind of fall into this. When you're like, all right, well, what's the force acting here? You have to talk about your perpendicular forces, your downward forces, your opposite forces. I'm not going to get into that in this course because I'm not a physics teacher, but it's all just the same coin, just different sides. So you've got to memorize that formula that I highlighted. I just don't want to leave it highlighted on my notes. You can highlight it in yours, but I'm leaving it that way. All right. So now we have a way of making a vector, whether we're given the size of the vector and its angle or the components. Because if you're given the components, you can derive the angle from that. All right, so example, what are we up to? 6, 5. And for A, if the length of the vector, if the magnitude of the vector is 6, and the angle is 60 degrees, find the vector in standard form, which means the AI plus BJ form. All right, so we just got to find, some people like to write what the A and the B are if they really, really, really want to. It doesn't have to be done that way, but some people might say, well, A, the X component, would be the magnitude times the cosine of the angle, which is 6 times the cosine of 60 degrees. Now you are allowed calculators at this point. It happens to be that cosine of 60 degrees, we do know, we can figure that out because it's a 30 or a 60 or a 90 or a 15 or a 120, all those angles that we have practice with. And the cosine of 60 degrees turns out to be a half. So that's 6 times a half, which is 3. You need to see that. Here's 60 degrees, here's 30 degrees, 1, 2, square root of 3. Cosine is the 1 over the 2. For the B, the y component of the vector, it's the magnitude times the sine of the angle, which is 6 times the sine of 60 degrees, which would be the square root of 3 over 2. So that's 6 times the square root of 3 over 2. 6 divided by 2 is 3, so that's 3 square root of 3. Now, I didn't say to use any decimal approximations for this, so this is actually the answer. If I give you something with 30 degrees or 60 degrees, I expect exact answers. So our vector, it's just AI plus BJ, so 3 times the I vector plus 3 square root of 3 times the J vector. I did not say round anywhere. If you said, what is 3 times square root of 3? So if you wrote 3i plus 5.2j, that's wrong. 3i plus 5.196j, that's wrong. I never said round. Usually you're rounding. Almost all these problems you're rounding, but I didn't say to round that one, so don't round that one. You know how to handle 30, 60, 45, 15 even. I wouldn't do 15 in a problem like this with an exact answer because now we're throwing the sum and difference formulas in it as well. I'm not saying it doesn't exist in the real world. I'm just saying I'm not that mean on a test. All right, for B, let's say the length of our vector is 11 this time, just to be annoying with all those absolute value looking symbols. And our angle is 192 degrees. Find the vector to 1 decimal of accuracy. So that time I did say to round it. So if you want to break down the A and the B separately before you just go straight to the vector, you can, but you can just go straight to this and go 6 cosine of 60i plus 6 sine of 60j. That would have worked as well. But I'm just doing it in a more meticulous way. So A would be 11 times this is the x component, times the cosine of 192 degrees, which we're going to round to 1 decimal place. That's 11 cosine of 192. Oh, Mr. Beckner, we can't use 192. Yes, we can, because we're not talking about inverse cosine. I also did not type cosine for some reason. What happened there? I clicked that instead. cosine 192. I'm going to double check and make sure I'm in the right mode. We are in radians, not degrees, so that would have been a wrong answer. And we can close our parentheses for good measure. And we get negative 10.75, blah, 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 so negative 10.8. The b, the y component, would be 11 times the sine of the same angle. So 11 sine 192. And we get negative 2.28, blah, 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 so negative 2.3. So our vector in component form is negative 10.8i minus 2.3j. Now, I didn't ask you to draw this, but you certainly could if you wanted to. So negative 10.8i would be going left about 11. So if, let's just say this is negative 10.8. We're really going to cheat the system. And then down negative 2.3. That says our vector would be pointing at that. Ugh, that's a little ugly, isn't it? Let's try harder. Go slower. Slow is fast. Fast is good. There's our vector. And you can see that that's a pretty good representation of 192 degrees. And the length of that vector would have been 11. So that length right there, if you really wanted to label it, that's 11. And this angle right here was the 192 degrees. Easy peasy, nothing complicated, but if you forget the formula, that might harm you. However, it's not like this is really a crazy formula because that derivation I did is everything. If you forget this formula, just draw up a vector, make your a and b the x and y components, and then just do this quick little algebra trick. Just write the definition of sine and cosine in terms of this, clear the denominators, because that's a pretty common technique that gets us somewhere, and boom, you get your formulas. I have emphasized over and over and over and over and over how much I'm not a big fan of just blatant memorization of formulas. Sometimes that's all you got. But if there is a logic and reasoning, an A to B to C to D to get you there, that's what math is more about to me. You might not ever use this type of math again in your entire life, but I've taught you, in my opinion, how to think logically, how to put pieces of a puzzle together. I've never thought a traditional algebra course or trig course or calculus course for a student who's not going to do this in the real world. They were teaching that material just to teach them some silly material they'll never use. It's to teach them a way of thinking. All right, so we did A and B. All right, next up. Given a vector in component form, am I on time? I'm getting close. Given a vector in component form, which means we give you it like this, the A, I, that looks like a J, doesn't it? I plus B, J. To find, this is a semicolon, not another J, that's a semicolon. I know they look the same. To find the direction theta and magnitude, which we've already done this one, just draw a triangle again. I mean, yes, there's a formula for this, and it is the magnitude is the square root of a squared plus b squared. Again, that's nothing new. But the angle is going to end up being the inverse tangent of b over a. And I'm going to put a special note here in red. Watch your quadrants. Remember, inverse tangent's only good in quadrant 1 and 4. So if your angle is actually in quadrant 2 or 3, if your vector is pointing in 2 or 3, you might get an answer that's in quadrant 1 or 2, excuse me, 1 or 4, and you would have to just use it as a reference angle and put it in 2 or 3. How do you know which quadrant you're in? The A and the B tell you the needed quadrant. Now, where did that, we know where the Pythagorean formula came from. Where did the tangent formula come from? All right, so again, the hypotenuse I'm illustrating as my vector. So that's its magnitude. Here's your angle. Again, I'm drawing this in quadrant 1, but it works for all quadrants in terms of an image. All right, so we don't know the magnitude initially, so let's not try and use that to find the angle. So here's an angle. Here's two knowns, the A and the B, so let's go with tangent. The tangent of the angle would be B over A. So that says the inverse tangent of B over A is equal to theta, if you just take the inverse tangent of both sides. But again, only in quadrants 1 and 4 will you pick up the true answer. So in other words, if your angle goes left and up, that puts you in quadrant 2. Inverse tangent's going to spit out something like negative 30 degrees. Just take the 30 degrees, make it your reference angle here, meaning that that angle is really 150 degrees. Inverse trig functions always have complications like that. We've seen it time and time again. Is it something that's happening every single problem? No. Is it something that's happening in maybe 10, 20% of problems? Yeah, actually it is. So please be careful with that. The most commonly made mistake on test 3 is not paying attention to quadrants dealing with inverse trig functions. It was an issue with the inverse sine, because that only picks up answers in quadrant 1 and 4. When we were using law of sines, we said we couldn't pick up anything bigger than 90 because of that. That was one issue. It's an issue with vectors, trying to find an angle given the component form, because if these components put you in quadrants 2 or 3, this inverse trig function, when you put it in your calculator, it's going to think you're in 1 or 4 instead. All right, I think I got just enough time to do an example before I pause for a few minutes. Example 6. If your vector v is negative 4i plus 5j, find its magnitude and its direction theta. Well, its magnitude we could have done before everything we just talked about. It's just the square root of the a squared plus b squared. Is this good notation? No, it's not, because my negative I don't have wrapped in a parentheses. Because negative square root of positive, so that's the square root of 16 plus 25, which is 41. Now, sure, if you want an approximation of this, it's 6 and some change. What, like 6.4? Man, that's a good estimation. I always was good with those. 6.4. So that's approximately 6.4. I didn't say to do exact, I didn't say to round, and in fact, I actually prefer a combination here, which is why I left those details out. But in my math lab, just pay attention to their instructions. The direction, we said, okay, yes, there is just a blatant formula you can memorize. However, if you conceptually understand trigonometry, if you forget this formula, just draw up your little right triangle. Understand that we have the B and the A. This we might have rounded, so it might not be a good idea to use it. Yes, we can, but it might cause error propagation. Small errors become bigger errors. And then you can say, oh, okay, well, if I know these two, that's opposite, adjacent. Let's use tangent. Opposite, adjacent. Oh, well, I need the angle, so inverse tangent, boom, nothing new, conceptually. All right, so theta should be the inverse tangent of B over A, which is 5 over negative 4. Now, I am going to have to round this. That is an exact answer, but it's not really a good exact answer because it doesn't describe the true quadrant. So this absolutely must be rounded. Check this out. Inverse tangent of 5 divided by negative 4. And we get negative 51.3, let's round to the nearest tenth. Negative 51.3 degrees. And someone, I'm pulling out red for a reason, someone might say this is the answer. But think this through. Pay attention. Be careful. My suggestion to you is to draw the vector so you know which quadrant this was really supposed to go in. Negative 4i means you're going left, 1, 2, 3, 4. 5j means you're going up, 1, 2, 3, 4, 5. So here's the point that the vector points to in standard form. That's in quadrant 2. Negative 51.3 degrees means you're going clockwise here. This would be negative 51.3 degrees, which is in quadrant 4. So it's wrong. This is a quadrant 4 answer that we need to convert in quadrant 2. So theta prime would be 51.3 degrees. You just cut the negative off. As long as that's less than 90, absolutely less than 90, you can just take the negative off because this would be negative 51.3 degrees, which makes the reference angle positive, 51.3 degrees. So let's put that over here, which means we'll have to do 180 minus theta prime, which is 128.7 degrees. Yes, that is the actual angle, along with the exact and rounded answers for the magnitude. All right, that closes out the section for vectors. And my phone call is about to come in. So we'll just hit save on that. Yes, okay. So give me about 5 minutes. I will be right back and we will start on 7.7. In fact, what I'm going to do is this. I paste that perfectly. Go ahead and start copying these notes down and then I will explain them when I come back. That's 7.7, the dot product. All right, easy. All right, so last section for test 3. Trucking right on along. The dot product and going right to the definition of what the dot product is. We call it a dot product because you're going to put a little dot between the two vectors implying multiplication. So this right here, has to be a dot. You know, we have that x is a multiplier, like 5x7 is the same thing as 5.7 for real numbers and for imaginary numbers. But for vectors, they're not the same thing. If this was a vector times another vector, this would not be the case. So please understand that these two different notations for multiplication mean very different things in the land of vectors. We have a dot product, and then another thing that we do have, but we won't be talking about in this course, is the cross product. This symbol is used for a cross product of vectors. And again, it is something different. So a dot versus an x between your two vectors means something completely different. A dot product is just this right here is the product of the x components. And this right here is just the y components being multiplied. So this is also known as a sum product because you're going to multiply the x components, then you're going to add, you're going to multiply the y components. If we were doing this in 3 dimensions, then you would add and you would do the z components, the 3rd dimension components. So the vector u we're calling its x component a sub 1 because we got 2 vectors. So then vector v has x component being a sub 2. And then conversely, the y components are b1 and b2. Now you might say, well, Mr. Beckner, why do you need to call them u and v? Why not just call them v1 and v2? Actually, yeah, you can certainly do that. Instead of going u and v, you can say v1 is a1i plus b1j, and then v2 is a2i plus b2j. There's nothing wrong with that. There's nothing wrong with just going with the subnotation for the vector labels in addition to the component labels. But in our course, we're usually given a u, a v, maybe a w. There can be a 3rd vector, a w. And then if I wanted to do u dot w, it would just be take the w's x and y components instead of the v's. That's all. All right. So the dot product. Notice in the actual process, this is what we'll do. We'll multiply the x components, we'll multiply the y components, and then we add. In this, there are no i's or j's. The answer is a number. It's not a vector, it's a scalar. Let me be more specific. A number, scalar. Scalar, 2 a's. The answer to a dot product is just a number. It does not have direction. Now guess what? The cross product is. That's right, you guessed it. The answer to a cross product is not a scalar, it's a vector. So we have a way of multiplying vectors to get just a number, and we have a way of multiplying vectors to get a vector as an answer. But it involves matrices, it involves the determinant of a matrix, and we haven't taught you matrices yet. We definitely haven't taught you the determinant of it, so we're not really ready to do that, nor will we even do it in this course. So the answer to a dot product is just a scalar. It's just a number. There are no i's, there are no j's. See, the a's do not have the I or j in them. Same for the b's. It's just the scalar. So scalar, 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 scalar. So here's the little note I talked about, the cross product. And then the whole reason we even do this at all, because we're very often looking for 2 vectors to be orthogonal. An orthogonal means that they form a right angle. Erase all the stuff I have circled. Two vectors being orthogonal means that they meet at right angles. So here could be your u vector, and here could be your v vector. But these are boring. These are pretty much just axes. And you could get, sorry, my mind just went blank for a second. You could get a unit vector in each of those directions, and because they're the x and y axis directions, the unit vectors would be I and j. Well, what if they don't start at 0 and 90 degrees? Maybe this is your u vector, and then this is your v vector. So I'm trying to illustrate that there is a 90-degree angle formed between them. So it just happens to be that if the dot product of two vectors is 0, then they form a right angle. They are orthogonal. Now you might say, why do we need another fancy word for right angle? Well, when we talk about right angles in 3 dimensions, it gets a little tougher to see visually because you're drawing on a piece of paper and your right angle may not be in the plane of your paper. And when you start talking about math in the 4th and 5th and 6th dimensions, you can't even really draw it up without your brain exploding. And if you can't draw it up, you're just going to have to be able to imagine this right angle formed thing somewhere. And we just go with a fancier name because 4, 5, 6 dimensions are much, much fancier. This is math with a top hat and a monocle on it, so to speak. So orthogonal means right angles. And a lot of cool things happen with orthogonal vectors. You can make what's known as an orthogonal system, which is really easy to just, instead of having your basis vectors go right and up, maybe they go at this particular angle right and up and this particular angle left and up. Maybe it's just that everything you're doing is always on this crooked axis, kind of like how our Earth is tilted on an axis. We're off by a few degrees. So maybe you would rather just do all your math in a world where, okay, your axes are slanted and this seems really goofy, but these vectors, you can make very, very, very nice unit vectors out of them and just very easily plot by going, 3 in this direction and then 5 in this direction, instead of going like 3.2 and I don't know, whatever the other number might have been. I'm going to just make those up on the spot. Do you have to have an orthogonal basis? Not necessarily, but we're not going to get into all that crazy 300 level. We call it linear algebra, but it seems a lot crazier than just regular old algebra. All right, so dot products. If it's 0, it's cool because it's orthogonal. It means those two vectors form a 90-degree angle and not necessarily just going straight up and straight right. They can be tilted. All right, so let's do a couple examples. Example 1, find the dot product. Then conclude if orthogonal. There we go. So for A, we're going to have 5i plus 7j. And for V, we'll have negative 2i minus 4j. The proof of orthogonality is not extremely difficult to do, but I think that when we demonstrate this with examples, it's going to be good enough to believe it. It's not like we're just pulling the quadratic formula out of thin air. So U is 5i plus 7j, V is negative 2i minus 4j. So the dot product, U dot V, we're just going to multiply the x components, which are 5 and negative 2. I'm supposed to be doing this in blue. Doesn't technically matter, but so 5 times the negative 2, and then we add. Now we multiply the y components, 7 times negative 4. 5 times negative 2 is negative 10. 7 times negative 4 is negative 28. So we can just write minus 28 instead of plus. And then adding those gives us negative 38. So that's the dot product. Because this is not 0, so not, I'm going to abbreviate this, orthogonal. Not the bug people ortho. That's it. That's the whole process. It's not some complicated process. It's kind of like doing a weighted average, the top of weighted average. If you're not familiar with that, then just ignore what I said. All right, for B, let's go with U equals 4i minus 6j. And let's go with V equals 6i plus 4j. Now, it's actually pretty easy to spot a pattern with orthogonal vectors if you do enough of these. I'm not going to spoil what the pattern is. I'd like you to use your own imagination to do that if you've done maybe several of these. But let's just do the dot product and see what comes out. U dot V. So multiply the x components, 4 times 6, plus multiply the y components, which is negative 6 times 4. Well, 4 times 6, each of those is 24, but one of them is negative, so guess what? The dot product is 0, which means, since it is 0, it is orthogonal. Maybe you don't believe me. Well, if you don't believe me, draw them up. Let's do B. Let's actually draw it. I didn't ask you to, but it's just kind of proof of concept. I could do better than that. Better. So let's go about 6 in each direction. 1, 2, 3, 4, 5, 6 as neatly and evenly spaced as possible, because the less neat and evenly spaced we are, the more our point might not be driven. And then 1, 2, 3, 4, 5, 6. 1, that's a little far. 1, 2, 3, 4, 5, negative 6. All right, so I'll do U in blue, 4i minus 6j, so that's right 4 down 6. So here's the terminal point of that vector, right 4 down 6. So there is the vector U. V I'll do in red, which was 6i plus 4j. So we're going to go right 6 and up 4, which is about here for the terminal point. And look at that. I think that's a pretty good depiction of a 90-degree angle. I can't prove that with the picture. Now, again, the proof is quite simple. I want to leave this to you to try and kind of imagine where this would come from, or you can look it up on your own. But I just want to say that the general proof relates to the slopes of perpendicular lines being m for the first one and negative 1 over m for the second one. They're negative reciprocals of each other. So the x and the y components give you a rise over run. So for this one, the rise over the run would be negative 6/4. This one would be 4 over 6, which are negative reciprocals of each other. So if these two things are negative reciprocals, then they're orthogonal. They form right angles. But it just so happens to be that that dot product arrangement of all those numbers involved, it just means if you multiply the x's, add, multiply the y's, if that's 0, that's the same math behind the slopes being equivalent. So again, I've really pushed you in the right direction of the proof of that one. I just don't want to completely spoil it on my own in my teachings. But hold on, I thought it was in the book. I actually don't see it in the book. Yeah, they do their proof in a completely different way, actually. But if you look on page 808, you'll get a proof of it. And they just do it based on the cosine of an angle, based on a formula we're about to get, which we haven't seen yet. Okay, so dot product, pretty easy to do when you're given the components. Notice what I just said. A dot product is pretty easy to do when you're given the components. Well, guess what I'm about to do? I'm about to not give you the components. Instead, we give you the angle and the magnitudes. And when I say angle, I mean the angle between them. So here's the alternate form of a dot product. Say you're given the lengths of the vectors. So the lengths would be the magnitude of u and the magnitude of v. Also, not necessarily plus, I'm not saying plus, minus, I'm just saying also, you're given the angle between them, which we'll call theta. Now, I'm not saying the angle formed from the positive x-axis to the vector, I'm saying the angle between them. See, here's the vector u maybe, and here's the vector v. I'm saying we know the angle between them. Maybe here's your vector u, and maybe here is your vector v. I'm just making a different example. Theta is not the vector from u to the x-axis. It's not that. Theta is not the angle from v to the x-axis. The theta here is the angle between them. It has nothing to do with the x-axis. Now, if I give you the angles for u and v, you can find the angle between them by subtracting them. It does relate to the x-axis, but it's just because it's a subtraction, that's all it is. So if given the lengths of the vectors and the angle between them, the dot product, definitely not going to show you this proof. The dot product is the magnitude of one vector times the magnitude of another vector times the cosine of the angle between them. Trust me, the proof of this will hurt your brain. It's on page 807 of your text. You've got a lot of little components, a lot of little algebra to take care of, squares of terms and things like that. But it does boil down to this. It would take us probably 25 minutes to explain that proof. It's not worth the time. So if I instead give you the magnitude and the angle between them, and I ask for a dot product, you got to use this formula. But admittedly, what we usually do with this formula is, it's for when we give you two vectors, maybe in component form, or maybe with their magnitudes, and you want to know what's the angle between them. So I give you this vector, I say this v is 3i minus 5j. I give you u, which is 2i plus 3j. And I want to know what's the angle formed between them. This is another thing that can be really important in physics, just having two vectors, two forces in different directions, and needing to know the angle between them. Well, these things have nothing to do with x and y axes. They're all in terms of their own kind of world. So what you do is you just take this formula with the dot product and you solve it for this angle. So you divide both sides by this, which is why these things end up in the bottom. That isolates the cosine of theta. And if you have cosine of theta isolated, then you just take an inverse cosine of both sides to solve for theta. So going from the top formula to the bottom formula is actually pretty easy. It's you divide by these things, and then you take an inverse cosine to get rid of that. And you'll be done. Okay, well, inverse cosine is only valid in quadrants 1 and 2, so you got to be careful, right? Actually, no. Because inverse cosine is only valid for angles up to 180 degrees, we're talking about an angle between two lines. When is that ever going to be bigger than 180 degrees? This is the worst it could be. If this is your u vector, and then this is your v vector, that's 180 degrees. If your v points down instead, then the angle you get is just here. It would be the angle between them still, just the smaller one. You might go, well, maybe I want the bigger one. Well, then do 360 minus it, and there you go. So the other case is if you're u, and I'm just doing this relative to an x-axis, that would still be theta, and it would still have to be, that's terribly written, it would still have to be less than 180 degrees. So this is kind of nice. This is very convenient that there's no quadrant issues with this inverse cosine. Inverse cosine has kind of been our friend for the most part. It saved our butts with the law of sines and cosine stuff because we couldn't have angles bigger than 180 degrees in a triangle. And here, when we're talking about the angle between two vectors, we're never even going to consider that angle being bigger than 180, because if one of the angles is bigger than 180, just say the angle between them is the other direction, the smaller one. All right. Example 2. Example 2. And we're just going to find the angle between the given vectors. And for A, we're going to do vector u. Let's go with negative 2i plus 3j. And for vector v, let's go with 4i minus 5j. So this formula, yeah, admittedly, it kind of sucks to memorize. I am another thing that I always do is take other formulas and memorize them and rearrange them, as you've kind of already picked up. Me, I hate when that happens. Me, I always memorize this formula and then algebraically solve for theta in the 2 steps I've already described to you. Divide both sides by the magnitudes and then inverse cosine it. This formula just doesn't seem as bad to memorize. So the dot product is the product of their magnitudes. I mean, I just feel like that seems like something easy to remember. And then a cosine of the angle between them. Why a cosine? Just trust me. So yes, there's blatant memorization no matter which of these things you choose to do. But this one, at least, it's easier to give you the dot product and the angle, whereas this one is a little more convoluted to get the angle. You take the cosine of both sides and then multiply the denominator. Yeah, it's the same 2 inverted steps. It's just how my brain worked. All right, so the angle between them. All I asked for was the angle between them. So the angle is, well, hold on. How can I do the angle? The formula says I need to know the magnitudes. This is the component form, this is the component form. So, Mr. Vector, you gave me a problem I can't even do. Wrong. You can. If I give you the components, you can find the magnitudes by Pythagorean. So first thing you got to do is find the magnitudes. So the magnitude of u is the square root of negative 2 squared plus 3 squared. That's 4 plus 9, which is 13. The magnitude of v is the square root of 4 squared plus 5 squared, which is 16 plus 25, which is 41. We're going to leave the decimal approximations until the very end, because if I put an approximation here, then I'm processing an approximation, and then we get error propagation. All right, so those are the numbers that are in the bottom. Okay, so now we're ready to go, right? Well, actually, no, we're not. We need the dot product. That's the top of this thing. So that's one more thing that we actually have to process. So second, find the dot product. Some people will just jam that all in the formula at once, and that's fine. So u dot v, excuse me, said dot twice. Multiply the x components, which is negative 2 times 4, plus multiply the y components, which is 3 times negative 5. That's negative 8 minus 15, which is negative 23. Okay, so our angle would be the inverse cosine of the dot product, which was the negative 23. Let me just pull back so you can see the formula. What the heck just happened? Dot product is in the top over then just multiplying the magnitude, square root of 13 times the square root of 41. Oh, we can't have square roots in the denominators, Mr. Beckner. Doesn't matter, we're putting it in a calculator. So we'll round this to the nearest tenth, per usual. Check your mode. We're in degrees, so it should spit out a degree. Inverse cosine, negative 23 divided by square root of 13 times the square root of 41, question mark, question mark, question mark. Is this going to be the right answer? And then close off the inverse cosine. Big question mark, big inflection in voice. Error in domain. Well, that seems kind of weird, doesn't it? Because literally every single one of these has an answer. There will always be an angle between two vectors, or it could be 0, but it would spit out 0, or it'd be a 180 and it would spit out 180. So if there's an error in the domain, something must be wrong. We're supposed to be dividing by, both these square roots need to be in the bottom, but our calculator, typing it this way, it does not think the square root of 41 is in the bottom because it's only dividing by the square root of 13. It thinks that square root of 41 is in the top. So that's actually not good. Why didn't that work? I need to go and, before I put that first square root, I need to open a parentheses. I'm doing this for a reason because people mess this up all the time. Then the square root of 13 and close it. Then the square root of 41 and close that. And close the inverse cosine square root. And what we get is 175 degrees, rounded to the nearest tenth. So these vectors are almost pointing completely opposite of each other. It's pretty close. They're only 5 degrees off. If you don't trust that, you can always draw them up and just see that your answer makes sense. What do we got? 5 in each direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'll do U in blue. That's -2 and then 3. Left 2, up 3. So here is U. We'll do V in red. 4i minus 5j, 4, 5. And because of my poor artistic ability, because I was not very meticulous with this one, it looks like it's 180, but it's not. Oh, I also didn't go down 5. That'll do it. Come on, stop that. All right, if I do this. Oh no, that's a classic rookie mistake I made. All right, erase instead. 4, 5. That looks a little better. So again, it looks like 180, but if you were really, really meticulous about it, you could see that this angle would be the smaller of the two sides, and that's where the 175 degrees would be. So if maybe we had a force pulling in this direction and this direction, because they're so far off of each other, if their magnitudes are close to each other, they practically cancel each other out. Think about two people pulling on a rope on opposite ends of it. But this actually says that one person is pulling from here, there's like a joint here, and then someone's pulling from this angle. And physically what happens is it causes this joint to move out until it's straight unless it's bolted down. But you get the idea. All right, if I insert a page, is this going to screw up? Yes, it is. Oh, dang it. I really don't want to have this on 2 pages. But if I hit enter, that happens. Oh, that's always so frustrating when that happens. Okay, here's what I'll do. I'm going to write B here. I'll open another page, and then it's fine. It's fine. U equals -2i plus 3j. V equals 3i plus 2j. Come on, I hit that 3 times. So it was 2i and -3j, correct? -2i, 3j. Okay, that's the first one. -2i, 3j. -2i, j. and V was 3j plus 2I. So you got to find the magnitudes, which would be, for the first one, the square root of negative 2 squared plus 3 squared, which is still the square root of 13. That's 4 plus 9. The magnitude of V would be the square root of 3 squared plus 2 squared, which shouldn't be a surprise. It's the square root of 13. 9 plus 4, 13. The dot product. Multiply the x components, which is negative 2 times 3, plus multiply the y components, 3 times 2. That's negative 6 plus 6, which is 0, which means, while I didn't ask anything about it, they're orthogonal. If they're orthogonal, that means the angle between them should be 90 degrees. So knowing that, I could go ahead and state that answer if I wanted to. I can say theta is 90 degrees and I'm done. However, let's ultimately prove it with the new formula. Let's practice. So theta is inverse cosine. And then we do the dot product in the top, which was 0 divided by. And then in the bottom, we're going to do the magnitude, square root of 13 times the square root of 13, which is actually just 13. But it doesn't matter because that's the inverse cosine of 0. I don't even need a calculator for that. Where is the x component 0 at 90 degrees and 270, but inverse cosine doesn't pick up 270, so it's 90 degrees. If you wrote 270, it would technically be wrong. My math, I would count it wrong. It's something I would count it right on a test. Actually, I take that back. I'm going to take this back. Hold on, negative 2i. They might actually say it's 270. That's a weird kind of, I don't want to say this. I don't want to say this. So if you drew up these vectors, negative 2i plus 3j, that's left 2, up 3. Here's your u. Then v is 3i plus 2j. So that's right 3 up 2. So there's the j, the v vector, excuse me. And we can see that that's 90 degrees. This right here would be 90 degrees, whereas the other angle out here would be 270. My math lab is supposed to take only the smallest ones. The real deal is that you take the smaller of the two angles between them. If for some reason, because I feel like a student brought this up to me last semester, or 2 semesters ago, but this was back in April and it's November, so I might be thinking of another issue. If you're on a test and the answer, if you think the answer is 90 degrees and my math lab comes back and tells you it's 270, for this specific problem, you let me know and I'll give you full credit. Because the way I was always taught is you consider the smaller of the two angles because that's just the way we like to think. But again, it's always, these are just kind of respective angles. If that's 90, the other's 270. If the first one's 100, then the other's got to be 260. You can just kind of keep going with that from there. All right. That will close out everything that we're going to do for the 2 sections of vectors, which are 7.6 and 7.7. So again, test 3 is only on 4 sections, 7.1, 7.2, 7.6, and 7.7. The homework for 7.6, you will notice that 3 or 4 of the problems I quote grayed out. I just made it so you don't have to do them. You're automatically given credit. You're more than welcome to do the help me solve this and see if you can follow it. But I didn't really teach you all of the ins and outs of that for 1 or 2 of them. The other 2 use bearings, which I really don't use bearings in this course at all, except for the beginning of the course. So that's why I've trimmed those out. You won't see anything about those homework problems in the test. So that's what the little star over 7.6 is just saying. It's a couple problems you don't have to do. Again, in the ballpark of 15 to 20 questions. I'm thinking 15, 16 questions because the stuff from 7.1 and 7.2 is quite lengthy. especially if there's two triangles from 7.1 as we had. And I told you, I guarantee you'll see at least one on the test. Well, no, not at least one, exactly one. Everything in 7.6 and 7.7 is extremely short. You're going to have more problems on vectors on this test than you will for the law of sines and cosines. I can guarantee that. So you'll probably have 5, 6 questions from these sections and then 10 or 11 from these two sections. Nothing was extremely complicated that we've done in vectors. That's not to say that there isn't anything complicated in vectors. We started kind of getting there with the dot product with the cosine formula, or inverse cosine, for the angle specifically. So there is a little bit of memorization. There is not going to be a formula sheet for this test. There is no formula sheet for this test. There is no formula sheet for this test. But you are allowed a calculator, because there are lots of decimal approximations you have to do. So make sure you have one that day. You still need to show your work. You're still going to submit it to me in Canvas within 15 minutes. You still email me and say, hey, check out question 4 and 13, and I can give you partial credit from there. I still reserve the right to go back and say, oh, well, they didn't show any work for this law of cosine problem. Where the heck did they get these numbers from? No credit. And I will absolutely do that on this test. If you don't have any work for anything from the first 2 sections, you're definitely not getting any credit. Vectors, there are some problems where you could conceivably not show work and get it right. So I'm not going to be as strict about that, but you better show good work for law of sines and cosines. There will be a review posted. Now remember, this date is going to be, the dates, excuse me. Come on, phone, open up my calendar, please and thank you. Because a week from today is the 25th. There's no class. 11/25. That would have been our test, but that's day before and day of Thanksgiving. So the test will be 11:30 and 12:1. We still have class on the 30th, that Monday. So you take the test on your own time. You all know how this works. Per usual, if you have any questions, please email me. Besides that, have a good day. Have a good weekend. Work hard. Get some homework done. 7.6 and 7.7 will be due same day as the test. I'd love to make them do that Wednesday, but I'll give you the 30th, that is. The next class a week after, that is to say. So 7.6 and 7.7 you'll see in my math lab will be due on the 30th. All right. Take care, everybody.